Hello everybody, welcome to lecture 13. This is the lecture for week 10 and it's my final formal lecture for the marketing research unit. I will continue with the tutorials at 12 o'clock on a Tuesday for half an hour. So if you're having any issues or concerns with your assessment that you would like to discuss with me, or you'd like me to demonstrate how things are done perhaps on SPSS, then feel free to plug into those or send me an email. I'd also really like to encourage you to provide your feedback on this unit. This is the first time that I've taught this unit and I'm quite new at it, so your feedback would be, particularly if it's good feedback, but any feedback's good because we'll continue to develop and evolve it. It would be really useful for me in terms of knowing what I'm doing right and wrong. So any feedback would be welcome. All right, okay, so getting into it, statistical analysis, I'm talking about association today. So we'll just get straight into it, I think. All right, so in this lecture, I'm going to talk about relationships between variables, okay? We'll talk about the presence, direction and strength of these relationships and correlation and covariation, how and when to understand when to use different types of analysis. Okay, the reading is the textbook chapter 14. I've got quite a few references to that in this lecture, so it's really worth having a good skim through that information to help you out to learn some more. All right, so again, we're still analysing data. We've jumped back up into step 10, and I think this is really the main. Now I feel like you're going to be quite well equipped with the main basic analyses that you need to conduct in SPSS, the main basic analyses that you should really understand how to conduct when you're doing any marketing research. All right, so we've spoken about descriptive analysis, inference analysis, difference analysis, and in this lecture I'm going to talk about association analysis, which determines connections between variables. I'm not going to cover predictive analysis in this unit, but based on all of the other information, you feel free to have a look in the marketing research textbook if you would like to learn some more. All right, so associative analysis determines where stable relationships exist between two variables. It's really important to understand that it needs to be a stable relationship. If it's always changing, then it's very, very hard to characterise it or make any business decisions based on the idea of a relationship. So there has to be some kind of stable relationship there. Okay, so a relationship is described as something that's consistent, systematic. It's a consistent, systematic linkage between the levels or labels for two variables. Okay, so we're pretty much talking just about two variables in this, the relationships between those variables. Okay, so levels are interval or ratio scales. Okay, so some sort of measurement where there's a defined distance between each measurement. And labels are nominal or ordinal scales. So a nominal, as I'll just remind you, is a named scale. So that would be, well, it's not even a scale, but it's a category. Okay, so in this example here, you can see there's fruit and there's a category of oranges, category of pears, and a category of bananas. And there's no existing scale between those things, but we might find that there's a relationship between whether people like apples and bananas more than to eat those together more than, say, apples and oranges, or pears and oranges in that case. An ordinal scale, remember, is where it goes from in an increasing or decreasing scale. In this case, hot, hotter and hottest. Okay, so it's an increasing scale. They're in order, as the word ordinal, but there is no defined distance between hot and hotter or hotter and hottest, so we can't say it's actually on a scale. Right, okay, now it's important. Now the reason I'm just reminding you of this is because it's really important, because we use different measures for the labels than we do for the levels, or for scales versus category data. Okay. All right, relationships between variables. Right, there's non-monotonic relationships, which is where two variables are associated, but only in a very general sense. For example, the presence or absence, for example, burgers and fries and strawberries and cream. Okay, so the presence or absence of one variable is associated with the presence or absence of another. Okay, so a burger and fries, there is a relationship between them because they're sold as part of a meal at most of the fast food places that we tend to frequent. So there is a relationship between them. It's not that they don't have other relationships with other things like fries and sauce, for example, but we're just interested in the relationship between these things and how frequently they occur together, for example. Okay, strawberries and cream, same example. I like food examples, so hope that's okay. All right, a monotonic relationship is that you can actually understand the general direction between two variables. Okay, so there's an increasing relationship, for example, as rainfall increases, this water tank would fill up, or a decreasing relationship, for example, as global temperatures increase, the Larsen ice shelf in Antarctica, it will shrink. So you can see that there are two different types of relationships. Okay, so if we're thinking about characterising these, we might look at it in terms of a linear relationship, which is a straight line relationship between two variables. This is probably not unfamiliar to you. I can imagine that you probably would have learnt a lot about these sort of things at school. I know I did. In the textbook, they talked about the relationship being characterised as y equals a plus bx. When I was growing up at school, it was y equals mx plus c. So it's the same formula, it's just got the symbols are just named differently. I think the textbook's American and I learnt mine in New Zealand, so I'm not really sure. But you'll probably know one of those anyway. So if y equals a plus bx, okay, y is the dependent variable being estimated or predicted, and it's always the vertical axis or axis. Okay, a is the intercept, which is where the line intercepts the y-axis. B is the slope, which is the gradient of the line. So you can see in the example on the left-hand side, the slope is positive, the gradient is positive, and the negative linear relationship, the gradient is negative. And there's another calculation to calculate that, but we're not really going there. I'm just making you aware of this. X is the independent variable used to predict the dependent variable, which is on the horizontal axis. Right. Okay. Then there's a curvilinear relationship. So there's a smooth, so this is characterised by a smooth curve pattern, and the formula can be really complex, and sometimes just finding the formula is actually the trick, because if you can find the formula for that, then you may be able to predict occurrences in the future. So you can have a positive curvilinear as shown on the left, or a negative curvilinear on the right. I know they don't look super smooth as it says, but that's probably how, when you're scattering in your data, that's probably how a curvilinear relationship would actually look. So we don't need to know the formula for that. Like I said, they're really complicated. I'm just letting you know that they're the different types, the sort of main types of relationships between variables. All right, so when you're describing relationships between variables, you need to consider some key factors, okay? The first is presence. Is there any systematic statistical relationship between the two variables? Is number one. Is it there? Number two, the directional pattern. Is the relationship positive or negative? Okay, is it going up or is it going down? The strength of the association is the third one. Is the relationship consistent and strong? Okay. So if you have a look at page 283 in your textbook, you'll be able to have a look at this. This is really quite valuable. This pretty much tells you exactly how you would go about analysing relationships between variables. Okay, so step one, you choose the variables you want to analyse. You identify the ones you think might be related. Okay, you determine the scaling assumptions of those chosen variables. This is important because you really need to understand if they're interval or ratio, so as I was saying, levels on a scale, or categorical, so named nominal variables, because that affects the type of analysis that you're going to do. So then, number 3, use the correct relationship analysis. For 2 nominal variables, which are distinct categories, i.e. apples and pears, use cross-tabulation. For 2 scale variables, use correlation, so preference. Scale variable might be desirability scales or preference scales, those sort of things, so on a Likert scale, for example. Okay, number 4, determine if the relationship is present. If the analysis shows the relationship is statistically significant, then it is present. Okay, then if it's present, so you first find out if it's present, as shown at the top there. Next, you find out the direction of the relationship. So a linear relationship will either be increasing or decreasing, and a non-monotonic relationship, which is what a nominal scale, so the named ones will require looking for a pattern, probably in a cross-tabulation, so a table, and you search for a pattern. Okay, and number 6, if present, assess the strength of the relationship. With correlation, the size of the coefficient denotes the strength, and with cross-tabulation, which is with nominal scales, the pattern is subjectively assessed, so you actually have a look at it and decide for yourself. I apologise for itching my nose, it's itchy today. Okay, all right. Okay, analysing relationships between variables, we're still on. Chi-square analysis, okay? So chi-square analysis is used with frequencies for the nominal scale variables in a cross-tabulation table. So in a chi-square analysis, I don't think I've written that properly, but it's correct. It's just the language grammar might be missing a word there. But the nominal scale variables are put into a cross-tabulation table to determine whether the variables have a significant relationship. So chi-square, nominal scale, named categories, right? Okay, non-monotonic. Okay, so you assess non-monotonic association in a cross-tabulation table based on differences between observed and expected frequencies. Now, this is important because I draw on this a couple of times in this lecture. The null hypothesis in these is always that the 2 nominal scale variables are not related. Okay, so if we reject the hypothesis, the null hypothesis means that there is an association, right? Okay, observed frequencies are compared to expected frequencies in chi-square analysis. Okay, so the observed frequencies are the actual cell counts in the cross-tabulation table, and the expected frequencies are the theoretical frequencies in each cell from the hypothesis of no association between the 2 variables. Okay, so this is from the textbook, and you can have a look at page 387. The expected cell frequency can be calculated by multiplying the cell column total by the cell row total, and then dividing by the grand total, and then the chi-squared formula is there. So you can use that to calculate it, but usually we just use the computer. All right, so the computed chi-square analysis compares observed to expected frequencies, as I said, but it's done usually using something like SPSS or some other statistical analysis. I think you can do it in Excel as well. The chi-square statistic summarises how far away from the expected frequencies the observed cell frequencies are found to be within a set of degrees of freedom, okay? And you can have a look at the textbook to read a little bit more about that. So R is the number of rows and C is the number of columns, and that's how so the number of rows minus 1 multiplied by the number of columns minus 1. The calculated value of chi-square is compared to table value to determine significance, okay? So you calculate the chi-square and compare that to the value in the table. SPSS and other statistical analysis programs compare calculated to table values and show the probability for support of the null hypothesis. Okay, so SPSS pretty much does that for you. A significant chi-square means that the researcher should look at the cross-tabulation row and column percentages to see the association pattern. All right. Okay, so to do it in SPSS, and I'll let you do this yourself, so I won't talk you through it in great detail. You select Analyze, Descriptive Statistics and Crosstabs, which I've shown you how to do in the tutorial already. In the Crosstabs window, you can select the row and column variables. Okay, so I'm just using my research as I always do. I've chosen the nominal variables generation, so that's baby boomer, generation, millennial, Gen X, etc., and accommodation, which will be like backpackers or hotel or resort, whatever. So they're both nominal categories, they both just have names. Okay, and then you click on statistics. So you select your nominal categories from the list in the left-hand side. You click on the arrow. Now the arrows, because they're selected, the rows and columns, the arrows are pointing left, but if I was actually in the left-hand column, they would be pointing right, so you can click on them to push them over. And then you click on statistics. Okay, in statistics, you can see here, this is what comes up, crosstab statistics. You need to just check the chi-square button or, box, and then press continue. Like I said, there's loads and loads and loads of different analyses you can do for various reasons. You might need to do those, and there's a vast amount of literature on why you would choose what you would choose, but in this case we're just going to do the basic, right? Okay, in the cells window, so you've selected the statistics window, then you need, after you've done the statistics, you need to select the cells window, and you can check row or column or both percentages or total percentages, just depending on what it is you're trying to find out. So this is just how it will be displayed in the table. And it just depends on what you want. So you click continue and OK to run the analysis, which shows up in the separate output window, as I've been explaining to in the other lectures. Okay, so here you come up with a cross tabulation at the top, which I have shown you before. I don't know, depending on whether you've seen that tutorial, you may have seen that. It also comes up with a chi-square analysis down here. Now, what this shows, okay, so on the left-hand column is the generation. So you've got millennial, Gen Y, Gen X, baby boomer and pre-war. And across the top in the columns, you've got motel, caravan park, resort, hotel, camping, backpackers. All right, so that's just how I designed it when I was putting those inputs in. And you can see here that I've asked for the percentages to be shown across the rows. So this is percentage within generation, okay? So this is not showing the percentage within motel. So the motel column percentages don't add up to 100. The rows add up to 100, okay? So what that 20% is showing me in the first top left figure cell is that 20% of millennials were staying in motels. As it turns out, there was only one millennial in that category, and so it's not probably considered representative, so I would discount that one because there's only 5 in the millennial category. However, Gen Y, I had 319 Gen Ys in my analysis, and you can see that within the generation, see, I'm just automatically picking out patterns here, 54% of the Gen Ys who we interviewed in Cairns were staying in backpackers. And 43% of Gen X were staying in a resort hotel, which probably reflects life stage. So you can see there's probably some patterns there, okay? Look at the chi-square test. This is what you're supposed to do first, okay? So we've actually got to identify whether there is a presence of a relationship first, number one, okay? I can't help myself. I see tables and I want to have a look at it, okay? But number one, if we're thinking about presence, we have a look at the chi-square. And we can see here that the significance, the p-value is 0.000, okay? So for the Pearson chi-square test, okay, remember that the null hypothesis is that the two nominal scaled variables are not related. Okay, so that's our null hypothesis. The chi-square significance value is very low, less than 0.05, so the null hypothesis is not supported, which means that there is a significant association. between these two categories. Okay, we can then, so when we say, okay, so we know there is a significant association, so that gives us permission to have a look at our big table, and we can examine the cross-tabulation to see where the relationships lie, which I already sort of got carried away with and started showing you. And that's how you do that. With a nominal scale, that's what you do. You subjectively assess, so you can see that there's a statistic that shows there's a relationship, and then you actually have a look and pick out what patterns you can see. And that's how you do that analysis. And you would write it up. First, I've established that there is a presence of a relationship through chi-square. Then I've observed the direction and strength of that based on who's doing what in the table. Okay, right, presence, direction and strength. So chi-square test. So I can identify that subjectively, but the chi-square test only identifies the presence or absence of association, okay? It doesn't tell us about the strength, that 0.000 statistic in the Pearson chi-square test, okay? It doesn't tell us about whether the relationship is weak or strong, or the direction is positive or negative. Okay, so a correlation coefficient, which is little r, is an index number between -1 and +1. It shows the strength and direction, so the number value. So if it's, say, -0.5, the strength is 0.5 and the direction is negative, okay, of the linear relationship between two metric variables, otherwise known as the degree of covariation. It also must be tested for statistical significance, okay? So covariation is the amount of change in one variable systematically associated with a change in another variable. Right. So the correlation coefficient, size and direction, okay? So here we go. If they're all over the place and you can't find any relationship in A, then there's no association. You can see that there's a cluster that moves down, and you can ask SPSS, or I think maybe even Excel, to create a best fit curve or line for you using the data that's already in there. So you can see a negative association or a positive association. Okay, so this is from page 394 in the textbook, so feel free to have a look at that. Okay, and here's some rules of thumb about correlation coefficient size. So you can see that if the coefficient is between 0.81 and 1 on the negative or positive side, the strength of the association is strong. And that goes down to where there is no strength of association. Okay, that's very useful when you're getting some figures coming out. Right, so to analyse correlation in SPSS, you select Analyse Correlate, and you can go to Bivariate. Now, I just want to make it clear here because I don't know if it actually says it. Okay, I think I said it earlier in the lecture, it's important that this is for scales, okay? This is not for nominal data. It doesn't work because there's no understanding of the distance between each value, so it can't measure correlation, okay? This is only for scale data, so ratio and interval data. Okay, all right, so you select Analyse, Correlate, Bivariate, all right? So this is just to do ours, which is our comparison. Okay, so select the variables you wish to analyse correlations between. I've chosen from my data again, images 1, 2 and 3, which is where people rated them out of 5 in terms of whether they dislike them or like them. And you need to have the Pearson correlation coefficient checked. And then that's it. So you select them from your list in the left, put them across into variables and then click OK. Okay, you click OK to run the analysis, which shows up in a separate output window as usual. Remember that as these are comparing with one another, only use 1/2 of the diagonal as it's repeated. Okay, so P1 compared to P1 is 1. It correlates 100%. So that can kind of remind you that that's not really a valid comparison. We're not interested in correlating things with themselves. So we can draw a diagonal and it's repeated. So P1 compared to P2 is the same as P2 compared to P1. See, 0.587 star star either way. So what this shows is that there's a significant correlation at the 0.01 level. So those double asterisks next to those figures actually explain that there is a significant correlation, and that's useful. And when you look at that, so we got 0.441 for P3 to P1. What's 0.441 here? 0.441 is between 0.41 and 0.6. So that's a weak association. Okay, so there's an association, but it's a weak one. 0.587 between P1 and P2. Let's just have a quick look. 0.587 is still weak. Okay, so there's associations, but they're not very strong. So this is, we can type this up. We can say there's a correlation coefficient of 0.587, which tells us that there is a correlation, but it's not very strong. So we've identified a presence and a strength. Okay. And this is actually the last slide. So it's important to consider these things. So that correlation assumes both variables share interval scaling at a minimum. So as I said, they need to be interval at least, if not ratio. It only takes into account the relationships between two variables, not an interaction with other variables. It doesn't demonstrate cause and effect, so you don't know why these things are happening, you just know that they're happening, and it will not detect nonlinear relationships between variables. And I think that's the end. Okay, all right, thank you very much.